Trusted your word. Trusted your word. Now I see through, just like all the rest. Trusted your word, believed your Lord. Now I see through, can't trust you no more. Trusted your word, believed your Lord. And now I see through, can't trust you no more. Psychologically abused since I was a kid. Believe in your stories, the things that you did. Now I'm asking for.
All right, we're
You're in the
live.
hot seat now, fan or whatever.
Way to open it with a strong sentiment. I guess we're live now, Alan.
Awesome. All right, welcome to the Ether Cosmology Celestial Theodolite Update number 8, hosted over here at Earth Awakenings. Thank you very much, Gio, for being a gracious host, always accommodating. All right, we'll get in with a quick recap of the process of the Celestial Theodolite, and then we will discuss briefly a summary of last month, or a couple weeks ago, there was a meeting on McToon's channel, so we'll do a little recap of that. And if there's any questions throughout the presentations that are going on tonight, if you have a question that is directly related to what's being discussed, feel free to jump in before the next thing moves on so you can get your question asked. If you have something else, wait till the open Q&A at the end there. And I think Jesse is also going to do a little prezi at the end here, so stick around for all of that. So to go ahead and get into it, the basic premise of celestial theodolite is that there are two fields, the visual field and the spatial field. Modern heliocentrism and the use of, as taught to us, how the globular proponents would like us to interpret the stars and the graticule and the movement of the stars and all that is through Earth curvature. And our assertion is that the spatial field and the visual field are not Euclidean. Now, they require it to be Euclidean for the purposes of how they teach it. So to find out the difference here, we're going to use star occlusions that intersect with terrestrial features, primarily mountain peaks. With a high enough elevation and a far enough distance, you can use this method to distinguish between a flat Earth and a globe. By doing raw trigonometric predictions, you can get what the relative angle to that mountain would be for an observer X amount of distance away, how high that elevation would physically be, right, if the Earth were a plane. And you can also subtract off of that elevation what it would be if the Earth were a globe, which results in two different times for when stars will get physically occluded by that peak. So the another important aspect of this is that it eliminates the refraction conditions between you and the peak, because as you know, only a physical object will cause an occlusion. We can show some examples of light being reflected through water and it not being blocked until it actually gets occluded by the object that's in the water. So you can kind of get a feel for that. But the important feature here is that those timings give mutually exclusive outcomes. So with the elimination of refraction between you and the star, you can make that distinction based off of the timing when we no longer see the star, because the refraction angle on that is going to be 0. Now, there's a couple other components to this, which start off with primarily we don't tell stellarium or any other references where we're at when we're doing the observation, right? We start with just calculating the relative angle to a mountain peak from some distance away. We then take that angle, we go into stellarium and we reference the peak of that mountain for the physical location, and then we look up at with the little reticule, and we match the degree that we calculated from our distance away. And when we see stars that intersect with that, we write those times down, and then we go back to our spot where we calculated the angle from, and we wait and we see if those stars get blocked at those times or if they get blocked at the time that corresponds to the globe angle. So hopefully that is a nice segue and recap into the process there. And a couple of quick notes about the use of stellarium, because some people will say, well, aren't you using stellarium? Isn't that a globe tool, et cetera, et cetera? Well, yes, you have to, but here's the thing with stellarium. Here's what stellarium actually is. Stellarium converts geocentric coordinates to geodetic coordinates. The geocentric coordinates are idealized ground positions of stars with respect to the first point of Aries taking zenith measurements. So these are like an idealized conception location for the star. And then then modeling that out further, they transform that observer to the center of the Earth, setting the altitude of the star to 3959 so that they can have their nice equidistant web around their celestial sphere and all that. It is not a globe tool in the way that it in the way that it's naturally asserted. It is a conceptual model that requires a fictitious observer at the center for reference for the comparison, and that's all that's being used there. So what's being asserted is that this conceptual model actually represents, Earth curvature and terrestrial features. So what we're doing is we're testing the angles to the stars to see if they are relative to the observer as a function of the globe, or if the angles are real, if they're intrinsic. If they're intrinsic, that means that if you go to enter the position of the star or where the observer is at, the globe is going to predict that the star is in a completely different location and outside of the confines of celestial refraction corrections to be applied. It it basically just shows that there's that the wiggle room, that the difference is made up in celestial and terrestrial and a combination of terrestrial and celestial refraction to make the globe viable, because it's essentially making these stars coplanar with the Earth. Now, if you can please hold your microphone, don't burst out laughing during the Prezi there, that would be great. And let's see, is Goose here yet? It's a little goosey goose here.
Nope.
Not yet,
Goosey is not currently here, brother.
but I'm screen
Not
sharing.
here.
I'm screen sharing everything that Shane posts.
Thank you, sir. Much appreciated.
Thank you, Jesse.
All right. I think that kind of covers my segue into the process and all that. So, Mike, if you want to go ahead and start with your screen share. Jesse, if you want to end real quick.
Certainly.
Thank you, sir.
Ended.
Sorry for the delay here.
No worries.
Should I screen share the document, the graph, spreadsheet? What do you think?
Start with the spreadsheet. Just explain it as you read from your document. I guess that'd be the easiest way, so that people can see what you're talking about. Or however you think it would be best to do it.
Yep, that way should work. I haven't done this in a while. Sorry.
No worries. All right.
Should have been easy. Is it there?
Nice.
Yep.
All right.
See a bunch of scary numbers. Looks very intimidating.
Scary numbers. I've based on a recent discovery, I've added a new column to the spreadsheet, column E. It's just got a little tilde for a column heading, but what that is an offset in seconds, which is the offset required to synchronize the final bearing. Well, in this case, this is uh, ours as viewed from the peak with atmospheric correction off. So that's the number of seconds it takes to align that with the of the peak. And what I did is I put a ruler on the screen of the video. I measured how wide the video was in centimeters. So it was 18.2 centimeters. It was 44, that corresponded to 44 arc minutes. So that's 2.417 something arc minutes per centimeter. And from that, I figured out where the peak was. And then I measured the star occlusions to figure out how far over they were, multiplied by that 2.4 arc minutes per centimeter to figure out what was the actual bearing of that star. So I watched the various occlusions on each video and came up with uh, offsets that align the final bearing on the video with the final bearing reported by Stellarium. Because what I discovered is all those little errors we were having from the very beginning. It started with Pike's Peak. We noticed they were like 2 arc minutes high. Well, that all turned out to be just bearing issues, where the frame wasn't quite synced up with Stellarium, and Stellarium is giving us a few seconds off. In some cases, quite a few seconds off, like the Greenhorn Mountain problem with it being 500 meters high. That was all because it wasn't on the right final bearings, because Stellarium was, it had the correct date, it had the correct time, everything seemed to be correct. But when it gave me the azimuth and elevation, the azimuth was wrong. And so this corrects the azimuth, puts it at the correct azimuth. And once that's done, everything magically aligned. In fact, we'll go to a little graph here. You're probably seeing the whole tab that the graph is on, rather than just the graph. But what this graph shows is, with the bearings corrected, the green line that's oscillating around the 0 is the measured deviation from what a flat Earth predicts, excuse me, compared to what was actually measured. So previously, Pikes Peak was about 50 meters high on average. I think 45, 46 or so on average. And now it's pretty close to 0. Let me look. It's 0.4. So it's not perfect by any means. But that was the closest I could get by eyeballing it on the screen with a ruler to line things up. And the red line on this graph just above the green line, that is what a globe Earth predicts is the deviation from what it expects with atmospheric correction on. And then all the way at the bottom, the magenta line, is the globe Earth deviation from what it predicts with atmospheric correction off. And interestingly enough, that is negative whatever the obscured height is. So for Pikes Peak, the obscured height was, which column is that in? Oh, sorry, it's not going to be on that column. It'll be on this one. So the obscured height is 201.8 meters. So roughly 202 meters. Well, you can see the magenta line that's about where it's hovering once the bearing has been lined up correctly. And then I added that 202 meters to the measured value with the atmospheric correction off. And that is the dashed dot magenta line that is almost a perfect overlay to the green line. Over toward the right side of the graph, you can see a little more deviation where it's not a perfect alignment. But basically what that's saying is, if you add the obscured expected obscured amount to the actual deviation what's expected, lo and behold, it comes up to 0. So in other words, what we're doing here is we're taking correction for the alleged curvature of the globe, removing that, and then it magically aligns with the flat Earth prediction. So that was a very, very surprising result. I did that initially for Pikes Peak, and then I did this whole spreadsheet, this 250616 version of the spreadsheet has all of the bearings, the initial bearings for the peak and the final bearings for the peak, and the initial bearings for the 2 observer tabs, all corrected to make the bearing right. And then that makes all of the data we've collected accurate. And you can see how that the globe Earth predictions are on either side of what flat Earth predicts. So the globe Earth prediction with atmospheric off, it reflects the 200 meters low because that's what Stellarium is telling us it was. And in the case of the atmospheric correction on, it reflects about 50 meters high because that's what Stellarium tells us the atmospheric correction is doing. And so that kind of explains why on the raw measurements, Pikes Peak was showing about 50 meters high because it had that bearing mistake built into it. So, and I'm going to go to my, I had a little description of this. My professors in graduate school, they were often complaining about my logical leaps, which were things that were so obvious to me that I didn't bother to explain it to them. And I'm just so this bearing mistake I corrected doesn't turn out to be one of those logical leaps. I'm going to explain to everyone the premise behind fixing Stellarium's accuracy problem that way. So in theory, what Stellarium is doing is it's taking the right ascension and the declination of the stars, and it's adjusting that for the latitude and longitude and the time to figure out what the azimuth and elevation are in that other format that we're using. So correcting the Stellarium data ensure that the bearings are approximately correct resolves that problem. If it had been anything other than timing, if it had been some other kind of internal error with Stellarium, then we would have had other problems. But as it turned out, aligning the bearings in Stellarium by a simple time correction was all it took to fix its mapping of right ascension and declination to longitude, latitude, azimuth, and elevation. And if it hadn't fixed it, then more serious internal errors would have been suspected. But that's literally all it took to resolve the big issues. Well, they weren't that big. We were having little unexplained deviations, which all turned out to be bearings. Because as soon as I fixed the bearings, the magenta line is telling us how big a drop globe Earth is expected to be providing, and it's in direct alignment with d squared over 2r. So we know we got it right here, and when we get that right, and then the green line is showing that looking at the elevation on the peak at the time the peak occludes the star does indeed accurately predict the height of that peak. In other words, we cannot refute the null hypothesis that the Earth is not a globe. So we can't come to the conclusion the Earth is a globe. We have to reach the conclusion the Earth is flat. So that's something interesting this spreadsheet shows. So I've got tabs for the first tab is peak with atmospheric correction off. The next tab is viewing from the observer location with atmospheric correction on. The third tab is viewing from the observer location, atmospheric correction off. And then the graph just overlays all of those so you can see the relationship of each of those quantities with each other.
We're not
I'm
hearing
sorry, can you hear me now?
you. Now we
We
hear you.
lose you? Yep. Yep.
Hopefully you heard everything I just said.
Nope. Missed it all. Or we missed.
Oh, darn.
No. We missed like the last 5 seconds, 10 seconds.
Okay, and the last after I went to the graph, I was looking for my notes about other things I wanted to be sure to mention. When the headings are properly aligned, one of the things you notice on the graph is that there's not nearly as much deviation around the zero line anymore, because it turned out that that was all based on problems with internal problems with Stellarium. Whatever calculation it was doing was producing the wrong heading, and since the heading and the sorry, bearing. I meant to say bearing when I said heading. When it
Azimuth.
calculated, yeah, when it and specifically not the azimuth, because the azimuth and the elevation are a side effect of right ascension and declination. And when it was converting right ascension and declination to the latitude and longitude that it shows, it was consistently getting the longitude wrong. There, in a few cases like Mount Rosa, it got it pretty darn accurate, but in most cases it was off, and it didn't seem at the time that it was that far off. And it wasn't until I adjusted bearings to get those dialed in that I realized they had a way bigger impact than we imagined that it did. Um, so it's important to double check those initial and final bearings. Final bearing if you're looking at elevation from the peak with atmospheric off, and initial bearing if you're looking at from the observer location with or without atmospheric correction. And well, I guess that was the end of the notes. So those I thought those were the most relevant takeaways from this. One other thing. So I started to, I first realized this when I was looking for what's wrong with what we thought at the time was Greenhorn Mountain, but it turns out it was actually North Peak that was occluding all of the stars. So I went to North Peak, and the yellow heading for North Peak on 51 is the incorrect data. The gray heading for North Peak starting on row 58, the peak, each of those stars was hitting, and that's what took 205 seconds to correct. And when it did that, the overall average deviation was 0.3 meter. So the first star, Ipupus, was about 17 meters low. The next star, PR Pupus, is about 11 meters high. And then the final star, HD 56813, is about 7 meters high, for an overall average of about 0.3 relative to the peak. After I discovered that, then I took a look at Blinn Mountain from Jesse's data, and I realized they had the same problem. It's off. Its bearings are off by about 92 seconds. The way Stellarium's calculating that, And when you correct that 92-second mistake to properly align the bearings, all of a sudden it's showing that um, it matches the globe Earth prediction uh, uh, at an average of about 2.5 meters low. And then Jesse's data, let me see, he had atmosphere off with his data changed to an average of 129 meters low, which is just about 2 meters higher than globe Earth predicts it should be low. Um, and with atmospheric correction on, at that point, it's about 162 meters high on average when it's aligned with the proper bearings. And then in the process of looking at all this, I also discovered why Jesse's, besides the bearing issue, why Jesse's data looked like it was such a good match, flat Earth prediction, and that was because that particular peak, as viewed from that particular observation location, makes the elevation from the peak with atmospheric correction off almost identical to the star elevation from that same peak with atmospheric correction on. And that creates enough as a difference between them that combined with the heading problem, they were pretty radically different. So I guess that's all I have to say about that. I'll go back to the graph because this is pretty fascinating that it's so much more accurate than we suspected. Oh, and this big yellow line, the wide yellow line in the center, that's the midpoint between the globe prediction with atmospheric correction on and atmospheric correction off. And initially, it had appeared that that was pretty close to the zero line, but after the heading was corrected, it dropped about 75 meters low with the proper headings for Pikes Peak. And then it's pretty close for Blodgett, Cheyenne Mountain, even Mount Rosen, Blue Mountain, and Green Mountain aren't that far off. There's a big problem at North Peak. You see all of the globe Earth predictions dip way, way low. And that's because according to Stellarium, that star is below the peak and we can't even see it at the time it was occluded. So Stellarium was obviously wrong on that. And then when we get to Jesse's data for Blinn Mountain, the yellow midpoint is almost perfectly right on to the flat Earth prediction. And that's because from that particular location, the peak with atmospheric off and the observer with atmospheric on is almost an exact match with the wrong headings. And then with the correct headings, then there's more deviation. Is there any questions about any of that?
Naturally, I have lots of questions. Hi, Doctor.
Hey, real quick,
Hi, Jesse.
before we get into Q&A, can we let Goose just got here to do his celestial theodolite? I'm sorry, to do his celestial refraction follow-up. Since we were just talking about celestial refraction, I feel like it would be a nice segue into the actual final like Q&A where we get to that. That
Yep.
would be cool.
Right, Goose? Before every answer involves celestial refraction, you can lay it out. That'd be sweet.
Yeah,
Hold
sure,
on.
yeah. Yeah,
And
Go
I'll
ahead,
have to
dude.
stop sharing, right?
Yes, sir.
Mhm. There it is.
Here, does Goose have screen sharing privileges?
Yep.
Okay, cool. Thank you, sir. Whenever you're ready, Goose.
Yeah, let's see, I'm trying, and then it's asking me stream in HD resolution with Nitro. No.
Just do regular res or whatever if you don't have Nitro.
Yeah. Oh, wait, what's going on here? Oh, here we go. Screen share. Is it working?
Yeah, Discord.
You
Yeah.
can usually either
Yep.
share by screen or by application. So this looks like it's sharing your whole screen. So either way, but yeah, we see your.
Oh, so you can see it? Oh, okay. As long as you can see it. Okay. All right. Yeah. So basically, I just wanted to like touch base on kind of like it's almost like a recap of the celestial theodolite.
All right. So sorry, real quick. It is a blank screen right now.
Oh, is it?
No.
Now we see the.
Oh, okay. Maybe it likes this screen, but it doesn't like this screen. Hold on.
Yeah, you can share by application instead of window because if you have two screens, it might be sharing on the other one. So if you go to,
Can you see that?
we do see the Discord panel screen. Yeah,
Oh, okay. Hold on.
you may have to just share the other screen if you want to show the other one.
Yeah, let me try
Yeah,
here.
just change stream.
Oh,
yeah.
they did? Oh, cool. I'm gonna get some chicken then.
JT.
Run Boston, you're hot.
Get me some.
I'm making JTZ. Enjoy that chicken though, brother.
My bad. Thanks, guys.
Chicken. All right, let's try
Better
that
than
again.
Goose.
Share.
Discord.
That's full Discord again?
Discord screen share part 3.
Jeez. I'm saying all applications.
Why don't you
Hold on.
just do it like your screen? Just do go up to the second tab and share your entire screen. Just have it. And then whatever you're looking at, we can see. Right, so I feel like you only have one screen. Is that a correct guess?
No, I've got multiple, but
Okay.
I just wanted to like share my. I'd be happy to share in my whole screen, but
Well, if you go to change stream, it should allow you to select which one you did.
Some applications full screen just goes black for Discord sharing though. It just sometimes it doesn't work.
can I just share my? Can I just share my like computer screen?
Yeah.
The whole window. I think maybe they call it window.
Yeah, it's
It's
risky,
called Win-
but it'll work.
Yeah, as long as you don't have any private stuff you don't want on the stream.
No, it's all good. Let's see. Share this window. Let's try that. Is that
Discord round 4.
Discord again? What?
Snake eyes again or whatever.
Come on here.
What's
No.
under change stream?
Yeah, go to
Yeah, I'll
change.
try that. Add a window. Maybe I can add a window. Stop sharing this window. Yeah.
Up at the top.
Oh, here we
Right.
go. Share entire screen.
Yeah, there you go.
Yeah.
Hey,
Okay,
look at that.
Now we got it.
Hey, okay. Yeah, so sidereal time. So yeah, so it's basically like the first point of Aries, the vernal equinox, and then it's at the observer's meridian, which is the zenith angle. So for 90 degrees. So right here, so you can just see like when that this is the star is always moving, like it's relentless. There's no stopping it. It's basically like a clock. So when that star, so you could almost take that star, like any star, and say, okay, 90 degrees. As soon as it passes that zenith angle, boom, start your stopwatch, and away it goes. And then that's directly related to time, right? So that's 360 degrees over a 24-hour period. and that gets you into, I mean, this is solar time here, but it's all related. You can jump in between the two. And then when we get into refraction, it's always lifting, right? So we got our, you hear that the sun sets 5 minutes. But you can still see the sun even though it's actually set 5 minutes away. So we're constantly lifting. Same with the stars. The stars are always lifting up. And then when we get to, so you see this pretty commonly, like when you get the atmospheric refraction. Can you guys see my mouse?
Yep.
Moving there? Yeah. So a lot of times you see like the mountain is drawn like right here. But you always have like 2 stars showing. So it's always like, it's kind of confusing. I've always tried to wrap my head around like what's going on with this diagram here. So then Jesse actually came up with, or showed me this Desmos, which you can actually take things and start drawing them into scale, which is super handy. So this is basically our celestial theodolite to scale, or the way I represent it anyway.
Wow.
And you can see
You're using the atomic second?
Am I using the atomic second?
Yeah, I just saw that in the literature you just shown.
Oh, well, yeah. So this is
International Atomic Time. Okay, that's it.
Yeah, I use UTC a lot, but then there's GPS. It's actually got like an 18-second deviation between UTC and GPS.
GPS does not ever have leap seconds, so it's become unsynchronized.
Yeah, well, I think it's because it works that way, just because it's sharing a common clock, so it's kind of like true within its own system.
Exactly.
Yeah. Yeah, so you can see this is the true star over here. This is our exosphere. And from our exosphere, if we keep on zooming in, you can see 2 lines here. So this is our straight plane trig line, and this is our bendy refracted line that's coming off that true star position. So when you bring it back, zoom in some more here. And then we can zoom into Pikes Peak. We've all heard of Pikes Peak. And let's see, we can start. So if we make this mountain angle here, well, here, I'll go over what I'm showing here first. So, so this occlusion, this is your true star position. And then it's tied to the apparent star position, which I call it umland. It's just a formula that I pulled out of a celestial navigation document that Alan had written by Umland. And in there he had a formula that's for less than 15 degrees. It looks pretty similar to Jesse's formula. I'm not sure. There might be some differences there, but yeah, so the occlusion, that's your plane trig, and then this is your refraction. We have a measure, and this just gives a delta between the occlusion and then wherever I put that. So I can use this to measure. We can see like the time difference between this point and this point. Right, where's the time difference here? Oh, right there. So you can see the seconds. So this is in seconds. So so this between here and here is 144 seconds. And then we got the peak. That's plane. This is plane trig peak, and then globe. This is Walter Bislam's, I think, formula I pulled off his website for calculating the raw globe. And then, which I also have a question about that at some point for a glober. And then and then here these are like Dr. Mike's measurements here, and they're all down here. So we got Pikes Peak. This is the distance, and then that's the height. This is all in meters. Greenhorn Mountain, etc. So if we put our T angle to equal the flat angle there. .5. And then we could even put it up. Well, yeah, we can leave it there, and then we put our T measure. Oops, sorry, our T delta at 2.6. And 2.7. 2.73. Right about there. So there's 53 seconds difference between that spot and that spot. Is there? Does anyone have any ideas why we're not claiming why flat Earth doesn't claim refraction? Well, then.
Because they don't understand that the speed of light depends on the index of refraction of air.
Well, yeah.
How dare you, Jesse? Einstein would be rolling over in his grave right now if he said that out loud. But real quick, it looks like the celestial refraction corrections are just making the star coplanar with the ground.
Oh no, we'll get there. Not yet. What I was thinking is that there's no measurements up here. Like there's nothing. There's no occlusions. There's nothing going on up here. So it can't be refracting there, right? Like there's no refraction happening there. If our peak, oops, no, I just moved it. Yeah, if our peak is occluding here, then the stars would be like, I don't know. There's nothing going on up here. So anyway, there's no measurements there basically.
Oh, the celestial refraction correction's putting it too high.
Yeah, it's too high. Yeah, there's nothing. So we would be like the stars would be. Yeah, there's just nothing going on here. So, but everything's.
Do any of these angles line up with actual measured angles?
Yeah, they do. So these are the measurements right here.
So the Theodolite measured this 2.5 or whatever you've got here.
Yeah. So see these blue collection of dots right here. These are the actual measurements. Yeah.
Okay, from Theodolite data, not from calculated.
Yeah, exactly. Yeah.
Okay. Yep.
So then if we put this guy down to our globe here. Oops. So now we're lined up with the true stars is lined up with the raw globe peak. Like this is the peak down here. And now this is where we're getting our measurements. So if there was refraction, so even if we were getting a timing of where's my measure here? Let's stick the measure on the. We'll put measure at where it's actually measuring. Even if we were getting a timing that matched up with this 66 seconds plus this, that would be like that would be a like that's a flat Earth occlusion, right? Because this at that point it would be our refracted light would be being occluded. Does that make sense? Because we need a physical,
so-
we need a physical object blocking our ray of light. We've got two ray of lights to choose from. We've got the true star, and then we've got a refracted ray.
So basically, according to this, if it is roundish, whatever the hell, it would have to be sufficiently larger to come close to this result.
Well,
If
yeah,
it was,
well, if flat Earth claimed celestial refraction, and we got this measurement, we could own this basically. Like we could still own this, because when you get to the if the raw globe is because if the raw like is so usually the globe position is that they claim refraction, right? So if we're not including anything down here. This is the true star on the globe. So they still have to, in order for the globe to claim refraction and the occlusion timing, then we have
according to the volume that we've been given to work with, the radius and whatnot.
Yeah, exactly. So because this is planar, this is a planar peak here, and this is the globular peak down here, right? And this is our path of light here, this purple, right? And this is the true star position. So if we're watching and getting our timings, and we got measurements here. So would the globe be predicting? Would the globe not claim celestial refraction at that point? You see what I'm saying? Like if they're going to claim celestial refraction, then they can claim it if they want. But we got 2 points where it lines up with flat Earth, and we haven't hit a globe occlusion yet. Because the actual physical peak on a globe is down here, not up here. So then if we carry on, so if we're gonna stick with refraction, which is fine, we can generate whatever refraction values we feel is correct here. And we move our, see how we're going to get that to 2.1, 2.15, no, I'm going the wrong way, 2.0. So right here, this is a globular refracted occlusion, which is fine, but we have a time delta of over, was it 2 minutes? That's gone by from here, from our top measurement.
So are you saying that the occlusion would be 2 minutes later?
Yeah, well, 122 seconds, so like whatever that works out in minutes, right?
2
Yeah,
minutes,
it's 2
and
minutes,
2
2
seconds.
seconds.
So then
Yeah.
it still doesn't help them, is what you're saying, at all, in none of these
It doesn't,
situations.
yeah, refraction. Like if I was a globber, I would stop talking about refraction.
So even though it sounds good, when I object with things like refraction, right, then that doesn't actually move the position to coincide with an occlusion on any of these observations. Is that the overall?
It makes it worse. You start like if you want to claim if you want to claim refraction, then you gotta wait because the star's been lifted, so it's going to take up more time for that star to be occluded.
Well, on their diagrams, they do the same thing, but they just make the line bend, and they're like, "Look, boom, flat Earth angle is my angle. Got it."
Yeah, well, they always draw 2 stars.
Ah,
So, but if you have to kind of accurately portray the situation as best you can, you're left with
That's the old
trying to
two-star
find all the
illusion.
light. You're trying to find all the light off of 1 star.
The old 2-star illusion, is that what someone said?
Yeah. Yeah, if you portray it in the diagram like that, it is very confusing. You're right. Seeing it to scale, it's crazy. And with
Yeah,
one
and then
with one position, it's just
and then
unlucky.
you just unlucky, yeah, and then the clock is always ticking. Like you can't stop that sidereal time. Like if you don't catch it here, then I guess the Glober would have to, they would have to catch it way down here, like 2 minutes later.
so that
On pipe speed.
explains why they're trying to add refraction at both ends. That's how you get that line to bend out of reality. You refract it twice. Oh, I got it.
Bend
Cool,
up
and it still doesn't work.
bend up and then back down.
Yeah.
So yeah, that's basically it for my scaling.
This model is awesome.
Thank you so much for
Yeah,
that.
this is great.
And much appreciated.
Yeah,
Does anyone have any questions for Goose before we turn it back over to Mike and Jesse?
Oh, Goose, could you put in specific numbers from my observation in there and see how it predicts? So it's
Sure.
I've got observer, target height, and distance in kilometers ready when you're ready.
Yeah, I can do observer height.
Oh, you want it in feet or in kilometers?
Meters if you got it. Yeah.
Okay, observer height is 3 meters.
Yeah. Distance in kilometers?
40.86.
Yeah.
And then the target height is 650.4 meters.
Sorry, say that one more time.
650.4.
Decimal 4?
Yep.
Let's find our mountain. Where'd it go? And then you want me to put so we got an angle of 0.907 for planar. Do you want the globe?
Well, I'm not exactly sure what your simulator does. Can it tell me what does it? I'm not sure what it's telling us actually.
Oh, okay. So we're just basically it's just like a scale model, trying to accurately represent the celestial theodolite to scale. And then you can take and then we're showing like the apparent angle of the star, and then we're showing the true angle to the star, and then we have a planar peak, and then we have a raw globe peak, and these are both like the predictions.
Oh, okay, so it doesn't really test the method or anything.
No, I'm not doing any statistical analysis. I'm just getting a visualization on.
Oh, it's a lovely visualization.
Thanks. But you get to see how, but the visualization kind of helps show you how celestial refraction is not helpful.
Oh, it should tell you how much he had to time shift my measurement to make it fit flat Earth, right?
Yeah, it does that.
Okay, cool.
So yeah, so you want. So like if say like we had a glob prediction, and then we had our T delta. 0.7. Oh, and I'll move it up to oops.
I believe it was 9.77.
Yeah, I'm just trying to get it onto the refraction spot there. I guess I could do like, well, sorry, Jesse, what did you ask again? You asked for the prediction between flat Earth and the, so it'd be
Yeah.
44 seconds, right?
I think he
If
shifted
if,
mine.
if we were taking like the celestial theodolite at its face value, that it's gotten rid of, like celestial refraction isn't a thing.
He
You'd
shifted
have
mine 92 seconds to make it fit.
Sorry?
He shifted mine 92 seconds of time to make it fit.
92 seconds? Like which way, positive or?
Mine were rising, so it was positive, but his were all setting and his were positive. So mine was actually the effective opposite sign of his because mine were rising, but I'm not sure if that helps.
92 seconds from 44? Yeah, I don't know. I'd have to look at it more, I guess.
It's no big deal.
I haven't looked at, I kind of missed most of Dr. Mike's presentation there. So. But yeah,
Well, thank
anyway.
you.
Oh, and then, so one question about this raw globe question, like this raw globe prediction. Like this is Bisland's, and as far as I know, it's kind of like the mountains are just sinking straight down into like a planar surface. Like, shouldn't this raw globe position be angled? Like, because our mountains are tilting away from us, right? On a globe.
Well, how are you calculating that?
Oh, I don't know. But I'm just like, conceptually, that's what's happening, or?
Well, I'm not sure.
Conceptually, yeah.
Yeah.
But the
okay.
effect would be the same or whatever.
Right.
Oh,
A 1 degree tilt away at 70 miles would be a very small change.
Yeah, okay. Okay, cool, thanks.
And if you're using a copy of my Desmos simulator and using my math for that, then I'm actually using the Pythagorean theorem, which actually does account for the mountain being tilted.
Oh, okay, cool, interesting. Yeah, I think I have that, so I'll have a look at that. Cool.
All right, cool. Well, thank you, sir. If there's no further questions, we will turn it back over to Mike and Jesse there.
All right. You still there, Mike? Dr. Mike? Oh, good.
Thank you,
I'm
Goose.
still here, ready for your question.
Thank you, sir.
Right. So my question, I guess, is it sounds like the method has been modified and there are now extra steps I need to do or that everybody needs to do when they're using it to accurately determine the true elevation, the physical elevation angle to a mountain peak. Is that right?
No, not at all. The method hasn't changed. We discovered, I discovered a bug in Stellarium. I don't know whether that would apply to any other astronomy tools or not. But it was observing that the final bearing was wrong, meant Stellarium thought it was looking at the star someplace other than where it actually was. And so the easiest way to, well, first I experimented to see, is this just a time problem or is this a bigger problem? Well, I quickly discovered, no, this is just, it's off by some number of seconds for no obvious reason, but all it takes is a time correction to correct the bearing. And then once you've corrected the bearing, all of the data is correct. And as soon as I did that, all of the data fell in line for both globe Earth and flat Earth predictions. So that's how I knew that that's the mistake Stellarium was making. It's going to take further research to figure out what's happening.
So I'm not sure what you mean by the azimuth was wrong or the bearing was wrong. For example, when I have a star and I literally see it occlude or rise right at the very highest point of that mountain peak, and I can see the mountain peak in the video, I can see the star rise, I can see that it rises at the highest point of that mountain peak. What does the azimuth have to do with anything? I know the exact time the star appeared or disappeared. I put that date and time into Stellarium. Does it not give me the correct true geometric angle using the originally defined Heffron method?
That's the problem. Your words indicate you understand what it's doing. It's pointing in the wrong direction. So it's telling you where the star isn't, and it takes some number of seconds, either plus or minus, to move that final bearing to where you actually saw the peak occlude the star. Or in your case with Blinn Mountain, it's unoccluding it, but it it once the bearing problem is fixed, that turns out to be just as accurate as a peak occluding a star. So we suspected that would be true, and fixing the bearing problem actually demonstrates that yes, that's true. It gives an accurate elevation in Stellarium once the heading is the actual heading where the star rose or set, as the case may be.
So when you say the bearing is wrong, what do you mean? Are you saying that how did you determine that the bearing was wrong? And wrong in what? Are you saying that Stellarium is reporting the incorrect bearing for the star at the time of occlusion?
That's exactly what I'm saying. Stellarium is reporting the wrong bearing for the star at the time of occlusion. And when you adjust the time to give you the bearing you can actually measure by putting a ruler on the screen and figuring out what the bearing is, once you adjust Stellarium to give you the bearing where the star actually occluded, then it gives you the correct um, uh, elevation for the star, but not until then.
But what are you comparing the bearing given in Stellarium to know that it's wrong?
Sorry, forgot to unmute. Uh, all along, I recommended that people use. I'm trying to remember the website. Let me look it up. There's
Peakfinder.org?
website no. There's a. Let me go to my peaks, bearing and distance. For quite a while, I've been recommending a website called movable-type.co.uk, and it has a /scripts directory, and in that is the latlong.html. And you can put in point 1 as the observer, point 2 as the peak that's doing the occlusion, and it will give you the distance to the peak, the initial bearing, in other words, the bearing that it looks like from the observer's point of view, and the final bearing, which is what the bearing looks like from the peak. Well, the final bearing from the peak was wrong on Blinn Mountain and on Greenhorn Mountain, and that's why those two were so far off. It was a little bit off on Pikes Peak. It was a little bit off on a few others, but I discovered that this is apparently some kind of internal timing error for whatever reason, as it converts a right ascension and declination into a latitude and longitude and tries to calculate the azimuth and elevation from that. It's apparently getting the latitude and longitude wrong, because what I was noticing, the longitudes were none of them were aligning properly. It was none of them was as, and quite a few of them were not aligning correctly with the final bearing. So when I made a few seconds adjustment in the case of Blinn Mountain, when I made 92-second adjustment, then it gave me the correct final bearing, and then which Stellarium calls azimuth. And then when it did that, then the elevation it gave was the expected elevation, or either from the peak with atmospheric correction off or from the observer with atmospheric correction off. And when it brought both of those two into alignment together and they both met their predicted values, I knew that was just a timing error. So
Can you
I can't explain it. We have to discuss. In fact, um, maybe Alan can help me. I lose track of time, but I think I just discovered this yesterday or the day before.
give that to me again real slow, and then I'll share it with everybody. The website address.
Yes, it is movable movable hyphen type dot co dot uk slash scripts slash latlong dot html.
How do you spell? Is it movable, like MOVABLE
Yes.
dash PIPE?
No. Movable dash type. Movable type, like on a typesetter, I guess.
Oh, TYPE. It was sounding
Yep.
like pipe, like conduit. Okay.
So my apologies for my mushy microphone or my impeded speech, whichever the case may be. That's it.
Okay, then you said scripts and
Lat long after scripts, lat long .html. Ocean. Autocorrect strikes again.
latlon.html.
Yes.
Maybe it's lat dash long.
Oh, there's a G in there. Sorry, I thought that said lotion. It says it's the G. And then it actually needs the L on the end.
I had an
I
L,
guess
but
this
I
is
was
some,
guessing. Okay, I was guessing without
yeah.
the L.
So that's precisely the site I recommend because it gives you everything you need to know on one page.
Okay, because I used a website made for surveying engineers that does the same thing. It lets you put in two coordinate sets and it calculates the headings, and it did match Stellarium pretty good. So, um, I can check this out and compare it and try to figure out what's up with that later. It may be making some small simplifications that cause a slight error. But anyway, I'll check.
Interestingly enough, when I used the initial bearings and final bearings from this website to align stellarium data with flat Earth and globe Earth predictions, um, match their predictions um, with atmospheric correction off. So I knew that was the problem. So another website that calculates a different value, it's a different value for whatever reason, but and maybe that's the reason Stellarium's off. Maybe Stellarium's getting its data from that website when it should be getting it from this one.
Well, it would be an extremely huge debacle if Stellarium were off, because people use it all over the world to aim their robotic telescopes at stars, and if it couldn't point a telescope at a star, that would, everyone would know about it and they'd fix it. So I'll have to check into this. But
People complain about that with Stellarium a lot, and we're talking about um, stars that are just above the horizon that are kind of used to those being all whacked out anyway. And long ago, I think they gave up reporting on those errors. And the errors we're talking about are usually in the neighborhood of a couple of arc minutes. So it's something the average astronomer with a low powered telescope might not even notice. A high power telescope would certainly notice it, but they're probably not using stellarium.
So I'm still not understanding what the azimuth has to do with the altitude angle. At the moment, let's. I mean, I get it. Are you talking about if a star arises kind of, not exactly on the peak of the mountain, you'll be measuring something less than the peak, and that'll look like an error? Or are you talking about a star that rises dead on the mountain? We can't use the original Heffron angle
Oh, no,
method.
not at all. No, not at all. Stellarium uses something called local sidereal time, and I think that's probably where it's making a mistake. Now, in most cases, that only makes a few seconds of difference. But if it's not getting the longitude correct, it's not getting that correct either. And that throws off every calculation it does. And it doesn't take much of an error to make 50 meters of difference. And typically, that's the kind of deviation we were seeing. So I tightened our deviations up from in the neighborhood of 50 meters to just a few meters. Or in the case of Greenhorn Mountain, it took it from 500 meters to with getting the um, longitude correct. Then it was sorry, I'm looking at the wrong tab. It got only it was only 1.5. Sorry, I'm looking at the wrong tab again. My apologies. I wasn't even on the right spreadsheet. Now I'm on the right spreadsheet. So with that correction, it's like 0.3 meter off. So it wasn't a very large area in Stellarium, but at that distance, a few arc minutes has a huge magnification vector. So it made a big difference in the final results.
So, just to be clear, when I see a star clip the peak of a mountain, can I take that time, put it into Stellarium, in other words, that time being the time that it actually clipped the mountain, put it into Stellarium, and put Stellarium on the mountain peak with atmosphere off, read the altitude angle, and is that the true altitude angle to that mountain, or is there some other steps I have to do for it to be accurate?
So what I discovered yesterday is sometimes it's accurate, sometimes it's not. And so the wise person will make sure that it's reporting the correct azimuth for that star, because sometimes it reports the correct azimuth, sometimes it's off to the left, sometimes it's off to the right. And so literally you have to what I found the best way to do it is put a ruler on the screen, calculate how many um, arc minutes per centimeter you have, or millimeter if you prefer, and then calculate what is the actual longitude of that star, and then make sure that's the one that Stellarium gives you for the time that you saw it occluded.
So, I'm not sure what the ruler
You just
has.
gotta double check your ASICs for measuring it's for measuring how much you're off or how much it could potentially be off. It's just for counting like the little reticles or whatever, right? That's what you were saying, Mike? Like the little things when you
Yep,
zoom in?
that's it. Yep, it's the sole purpose is make sure that Stellarium is telling you the correct azimuth for that star, the one that the azimuth you actually saw on the screen. And if not, adjust it a few seconds so the azimuth is correct. And once it's got the azimuth correct, it gets everything else correct.
All right, boys. So remember, check your ASICs.
So, if the star rises exactly at a mountain peak, and I know the lat long of the mountain peak, and I know my lat long, then I don't need the ruler, right? I can just put my lat long and the
You could
lat.
just eyeball it if you need more precision, then you get the ruler out.
I'm just not sure I understand the procedures correctly. I'm trying to understand the procedure because I want to be able to test it naturally.
No worries, no worries. Hit him with it one more time, Mike, and then you'll have to catch the replay and or follow up with emails or like do it on the next one. Okay.
So I'll be happy to. Basically, what I've been doing to make sure that Stellarium is not lying to me is I look at the peak on a map. I figure out where on the video I'm looking at the peak was. I measure. I've been measuring from the left side of the screen to that peak to find out how many millimeters is that. I multiply that reading by, in my case, is 0.2417 arc minutes per millimeter. So I multiply that out to find out how many arc minutes from the left of the screen is the peak. Now I can subtract that from the final bearing of that peak in Movable Types website. Once I know how much deviation there is of the peak from the left side of the screen, I can now measure from the left side of the screen to any occluded star, do that same calculation, number of millimeters times 0.2417 arc minutes on my screen, to figure out how many arc minutes that was off, subtract the number of arc minutes I got for the peak on the screen, and now I know what the deviation is, and then I can compare that to the azimuth that Stellarium reports for the star to see, is it at the right longitude for that star. And what I discovered is the entire video ends up being off by some number of seconds. So, like in Pikes Peak's case, for example, on January 27th, the entire video was off by 17 seconds. On January 30th, the entire video was off by 14 seconds. On January 31st, the entire video was off by 15 seconds. When I moved on to Blodgett Peak on February 7th, that entire video is off by negative 20 seconds. When I moved on to Cheyenne Mountain on March 9th, that entire video is off by negative 32 seconds. Mount Rosa was effectively zero, so it was right on. That's bound to happen, like a clock being right twice a day. Blue Mountain on March 12th, that was off by negative 15 seconds. Green Mountain on March 14th was right on. North Peak on March 23rd, that was off by 205 seconds. And then Flynn Mountain, your data on May 28th was off by 92 seconds. So the entire video was off by 92 seconds. And I'll emphasize again, this is within Stellarium. So this error is being made by Stellarium. And that's assuming that the time on the video are correct, which in your case you were playing WWV, and in my case I was taking it directly off the time server that the telescope was using. So those timings appeared to be correct, and in fact those timings worked perfectly for Mount Rosa and Green Mountain, but they were a little off for all the other mountains. And sometimes they were ahead, sometimes they were behind.
So if all of these variations in these timing errors from Stellarium were caused by Stellarium, then how did my formula predict all of those without using any code from Stellarium?
Well, if you look at what yours predicted, they didn't predict what you thought they predicted. So let me see. You had atmospheric correction off, right?
Yes. Yeah. Well, for using your method, I followed it strictly, which of course had atmospheric correction off. but when I put in the distance and height differences, can you see my screen?
Yep, I can see your screen.
Okay. Here in the top left corner, the red or the blue line is the difference between using your method and the arctangent of the rise over the run. So you can see Blodgett Peak was kind of low, Cheyenne was like kind of low, Mount Rosa matched almost perfectly, Blue Mountain was kind of low, Greenhorn was way too high, and then my two Blinn Mountain ones were way too low. So, but the formula, globe apparent angle minus astronomic refraction plus 1 degree per 69 miles, based strictly on observer elevation, mountain elevation, and distance, and that's all, predicted all of the Heffron method results within this red line close. That's how much this red formula deviated from the results you got. So somehow there is a massive non-random element contributing to the angle that your method gives, but it is modeled almost perfectly, well, within the noise, perfectly by this formula here. So it doesn't make sense that Greenhorn somehow read super high and Blinn Mountain somehow read super low due to some errors in stellarium, when this formula perfectly expected those errors. Does that make sense?
You may be onto a suspicion, what's been a suspicion of mine all along, that stellarium is specifically tuned to match globe results. So the errors that I witnessed may be no coincidence, but it was actually this graph of yours that inspired me to do the graph I showed earlier today, where not only the flat Earth prediction, but the globe Earth prediction matches perfectly. But the globe Earth prediction matches perfectly only when I take out the globe Earth expected deviation. So I lay it practically perfectly on top of the flat Earth prediction. If only I take out the globe curvature. If I leave the globe curvature in, then it's more similar to this. With the exception, as I noted, on Greenhorn Mountain, it shows everything way negative because Stellarium believes that star is not even visible from my location at the time it was occluded. I have to look up what it said. It said it was negative 26 arc minutes below the peak at the time the peak was observed to occlude it. And that's
From your
what
house?
led me right from my house. So it says it was 26 arc minutes below the peak from my house at the time it was occluded. Um, and while I was playing around with that, I accidentally switched to the next day. So I clicked it from March 23rd to March 24th. And when I did that, it lined up almost perfectly with where it was. And that's when um, at first I thought it was off by a day. But as I investigated this more and more, I discovered no, the problem here is it's not aligned up with the proper bearing. For some reason, it's giving me the bearing off, and so I went through my thought process of what can cause that kind of calculation error, and I decided to try time first because that's the most obvious and the easiest to test. So, and just skewing the time is all it took to fix absolutely everything everywhere. And so then I knew the only mistake they were making is they weren't correctly converting right ascension and declination to latitude and longitude based on what they thought was the local sidereal time. They were probably making that calculation wrong. It's a little hard to say. I don't want to exactly second guess them, but it's definitely a timing problem, and it's going to require some more research to get to the bottom of what's going on. And in the meantime, I think we can use other astronomical tools, or this is actually pretty easy to repair once you know that all you got to do is figure out what the azimuth really is and make sure that that's what Stellarium's reporting.
So I wanted to go back to this measuring of the heading or the bearing, because in order for this method to be something that anybody can go do, we all need to be able to understand it. And I figure I'm of average intelligence, more or less, and so if I can't, then half of people probably can't. So let me change my screen share here, with your kind permission. So I found a way to go to Peak Finder and download a Horizon file for Stellarium from Peak Finder. And so I did that for your location. You can see here's Greenhorn Mountain, here's North Peak, and you know, they're all, a lot of them are here. They don't always all show up, but it's pretty handy because then you can see, it gives you a reference as to where where the mountain peaks would be seen from your location. And what I found was that the stars you're listing on the North Peak are not anywhere near the North Peak, and that the North Peak wasn't even in your video unless you have video that I'm not aware of.
What's it show is the longitude for North Peak?
I'm not sure what you mean by longitude.
Scoot your cursor over to the right a little bit till it lines up with the beam from North Peak. So that's off by a couple arc minutes. The actual bearing is 201.07 and 54 arc seconds.
Okay,
It's a
right
little
there.
off.
What's that?
Right.
Okay, so there's 207. 201, oops, there's 201.07.
It should be 207, 201, 207, sorry, 201.07, 54. That's where North Park Peak actually is from my
Okay.
house.
Okay, so right there.
Well, it's
Right
not
where
very
the,
far off, but that's enough to make 500 meters of difference.
well, but the star was showing up somewhere in the middle here.
Well, as I said, what I did is I measured over to the peak to find out what is the offset from the edge of the screen to the peak. Now I have a reference point, and from that, I can calculate how far off is every other star occlusion from the left edge of the screen, and I can subtract the bearing of the peak from that, and now I know how much offset that is from the actual peak. Then I can compare that to what Stellarium is telling me the location that star is, and that's where Stellarium is making its mistake.
Oh, so you're not saying that North Peak was in the video, you just used it as an azimuth reference. Or are you saying that North Peak was in your video?
As I recall, it's been a while, but as I recall, North Peak was barely visible at the extreme right edge of the screen.
Oh, no, that wasn't North Peak. I looked at great depth into it. It was that bump about halfway between. Yeah, this, let me change my screen share again.
What's the bearing of Greenhorn Mountain? Could you go over there?
Yeah, sure. It says,
205?
what's that? 206.28 or so. Well, 205.58, about 206.
sorry, I muted my mic instead of unmuting it. So I'll have to go verify those numbers again. Let me do that quickly.
Yeah, I think I emailed you some time ago an overlay where I had identified the bumps in your video and showed that it was not including Greenhorn, or not including North Peak. It included Greenhorn on the left and then a bump in the middle that appeared on the right. A bump halfway between them or so that appeared on the right.
Yeah. So at the time you sent me that, I noticed that your bearings were a little off there, but I didn't think at the time it was enough to make any difference. And I also knew that at that time that North Peak was either not visible or barely visible. And I'm pulling up my bearings now. Apparently, I have this sorted by date and not by name. I'm going to change that so I can find it. Okay, so the bearing to North Peak is 247 arc minutes and 52 meters from my house. The bearing for Greenhorn Mountain is 199.47 and 44 arc minutes. So those are apart by pretty close to 1 degree. So yeah, North Peak should be not quite visible. And so I suspect what I did on that one is I measured to uh, Greenhorn Peak, which was known and visible. And then I knew the offset to that. And from that, I could still deduct that from everything else to find out what their bearings were. So it's a pretty simple technique, and it doesn't have to be done the way I did it. There's many different ways you could accomplish that same thing. But the key to this is figure out how far off stellarium is on the bearing it's giving for those occluded stars, and correct for that by aligning it correctly.
So, are you saying that at the actual time that the star clips that, clips that ridge line, that mountain peak, if you put that time into stellarium, it may not give the accurate geometric angle using your method, right? And that there's a second step that I have to do.
If you're using stellarium may or may not be correct, and it's shown that sometimes it's correct, sometimes it's off one direction, sometimes it's off another direction. So you do have to add if you want extreme accuracy, and you don't necessarily need extreme accuracy because you can easily tell what's up even if things are a little sloppy. But it for me, when I made it extremely accurate, that's when all of a sudden I was seeing things I was never seeing before, like the fact that the globe Earth prediction for atmospheric correction off was actually low by the amount that globe Earth would predict that the peak is low. And in theory, with atmospheric off from my location,
We'll have to see.
it's showing me where the peak
Oh, I
is.
think a star just peeked up.
We got a hot mic in there. If somebody could grab that real quick, thank you.
I got it.
I guess the bottom line is you don't need this extreme accuracy, but it's easy to obtain this kind of extreme accuracy if you're willing to do a little extra work.
Well, in my case, without doing this extra step, I got a perfect globe match. So, obviously, ordinary people like me need to do an extra step, and I'm not clear on how that could be done. To me, it looks like we're just putting in basically a fudge factor on the time and saying stellarium is off by anywhere up to 4 minutes, plus or minus, and fudging that until we get the flat Earth result we want. So I'm trying to understand what I need to do in my specific case of Blinn Mountain from Edith Hook to accurately do this. Does that make sense?
Well, I think you misunderstood something I said. This corrects not only flat Earth estimates or measurements, but it also corrects globe Earth measurements, because when I corrected it in this way, what the globe Earth says the elevation should be from my location, spot on to what it says it should be, 204 degrees, and 204 degrees is 200 meters lower than it should be, which was a known issue. And in fact, when you add the 200 back, you go to the zero line, which means it the globe Earth prediction almost exactly overlays the flat Earth prediction. The difference being that to make it that exact match, what was required is to add back d squared over 2r. In other words, add back how much the globe Earth predicts it should be low. And when you do that, it comes up to the flat Earth prediction. So in other words, the globe Earth prediction is wrong, demonstrably wrong, and is almost a perfect overlay to the flat Earth prediction. When you add back the globe Earth tilt that stellarium takes out for you. So I think this is a well-proven technique if you want the ultimate in accuracy. And don't forget, on my first measurement ever with Pikes Peak, flat Earth predicted it would be 2 degrees, roughly 31 arc minutes, and it was. It was actually a couple arc minutes high, but that was a radical deviation from what flat Earth predicted versus the 218 or so that globe Earth predicted. So there was no contest about which one was right. And I think the point of contention this whole time is globe Earth is achieving what it does by throwing in celestial refraction or terrestrial reflection or temperature adjustments, and the flat Earth predictions come up even more accurate without any of that.
Well, and can you see my screen?
Yes, I can.
Okay, so this is one of the stars in my series that was in the spreadsheet. This is the radio tower. Can you see my pointer? My mouse pointer? This here is a star that's just risen, 10 seconds ago, 8 seconds ago, whatever. And I played it a little bit past the rising point so that you could see it better because it was pretty dim when it first rose. You can see the mountain ridge line here. So this star basically rose extremely close to the very top of the mountain. And yet, when I put those times into stellarium, following your original method to the T, it gives me almost a perfect globe match. So what do I need to do? What's the next actual step I would do in this case to get the correct result? I know the latitude and longitude of the radio tower because that's published in the FCC database, and I know my observer latitude and longitude location because I was there and I averaged my GPS for like over an hour to get a good solid fix. What would my next step, and this is for anybody who's recreating this experiment, what would my next step be?
So you plug the
If
observer.
we get to the last time, we're gonna go over the last step for now. So,
Yeah, he's got a point. We've
but
gone
it's
over
already.
this several times. But
We'll
you
do it
can,
one more, and we'll move on to another subject. We'll wrap up soon because it's getting late here. And like I said, I'm not on the computer. I'm out in the field, as they say. So
Oh,
mountaintop. And so be wrapping up here. If there's any further questions or anything.
okay. So you go to the movable types website, plug in the latitude and longitude of that antenna. Use your ruler or whatever technique you want to use to figure out how many arc minutes is that star offset from the antenna, and then compare that bearing to what. Sorry, in this case, I was taking the bait of the star. You don't need the star. You only need the antenna. You've got the latitude and longitude of the observer. Plug that into movable types as 0.1. As 0.2, plug in the latitude and longitude of that radio tower. Since you know that, that gives you a final bearing. Now you see where the you do need to know where the star is. That gives you the you can now measure on the screen how far offset that radio antenna is at a known bearing. Now you figure out how many arc minutes offset that star is to the left of that. Find that star at the occluded time in stellarium and compare its azimuth to the longitude you just calculated it should be, and see how much in error stellarium was. Correct that so it gives you the correct azimuth for the star. And once you've made that correction, will also give you the correct elevation for that star. And then
okay.
that you can take the tangent of, multiply it by the distance, add it to the 3 meters observer height, and you've got how high it says that point was.
Okay, so for example, I believe the tower is 77 meters above the ground. So I could use that to figure out how many meters per pixel, and then I could determine the true azimuth of the star, and then I could slew the time in stellarium until its azimuth matches the true azimuth of the star. Is that basically it?
Yep, I'll tell you the same thing I always told the software engineers that I was managing. There's infinitely many ways to solve every problem, and please don't try them all. Just settle on one that's close enough.
I
Right.
have a question. It might be slightly off topic, but regarding light and stuff.
Go ahead, sir. What's your question?
I can't really tell if light is a wave or a particle.
Slightly off topic. Would love to get into that, but that is not the subject of this discussion at the moment. But
Yeah, I don't know.
if you send me a
If
DM,
we can
though,
get
I'll
to
get back
it
to you
at some point.
Here's
on
what
that.
we would
That is
call
my
a
favorite, one of
recursion.
my favorite subjects. So
Yeah, if
Uh,
at some point we can get to it, that's great. No rush, but
I do have two more different and very relevant questions, if I may at least try one of them.
yeah. Send it. If it doesn't take very long, we can get the second one too.
Okay. But two of them are kind of the same. Does the method only work on a flat Earth? Does it assume a flat Earth? And would it give the same results if Earth were a globe? Does it assume a flat Earth, basically? If Earth were a globe, would it also tell us that?
Mike, are you muted?
I muted. I just unmuted. And so this goes back to the null hypothesis. The whole purpose of the null hypothesis is to assume the opposite of what you believe to be true. So if I'm trying to prove the Earth is a globe, which I set out to do, I assume that the Earth is flat. So I come up with a method that I would expect to be true if the Earth is flat, and that's this method, and it does work for a flat Earth. But the purpose is not for that to work for a globe Earth. The purpose is to be able to refute that that works for a flat Earth, and that's the step that failed. As soon as I tried to prove it was wrong, what I ended up demonstrating is it was right. It's showing that the Earth is flat against all odds.
Well, does the method assume that the altitude angle to the physical, the true
It doesn't
physical?
assume anything, bro. It's just you know what it assumes. It's two calculations. It doesn't assume anything.
Well, does the diagram show that the altitude angle of the star is the same, the true geometric altitude angle of the star is the same for both the observer and from the mountain peak?
So on the, I released my Starlog 2025-06-16. I posted it to main chat on the Ether Cosmology forum. And if you go there, what you'll see is the angles are all flat Earth angles. So it's showing that all the angles came out flat Earth angles with no exceptions. So it's failing to refute the null hypothesis, which leads us to believe that the hypothesis that the Earth is a globe is incorrect, and the Earth actually appears to be flat.
But with
So,
respect to the stars, how be? Are there any other questions, Jesse?
well, I don't believe my question was answered. Is alpha lower and alpha upper the same angle in this diagram?
Geometrically, for the observer at the furthest location away, right, that first alpha, if the timings match up, then alpha is equal to alpha geometrically. That is the implication.
If the Earth were a globe, would alpha be equal to alpha?
With respect to a different timing.
No, I mean, at the same time, if you were measuring with reference to plumb at the target location and reference to plumb at the observer location, those two plumb lines on a globe would not be parallel, so alpha would not be equal to alpha, right?
If the occlusion timing matched, then it would be. That's the implication there. So are you referencing how the globe predicts two different positions or two different true positions for the star with respect to observer location? Is
Well,
that kind of what you're getting at?
well, with respect to observer and target location, because
Right. Okay. Yeah. Okay. So
stellarium,
no, you would have two different angles, but you don't have but it would still correspond to a different time for that intersection. So like that's the important part to remember. Is that if alpha equals alpha, then the geometric implication is that it's flat. If your timing was lower, then the implication would be that alpha doesn't equal alpha, but you would have the timing that corresponds to your measurement. Does that answer your question, sir?
yes, thank you. So, doesn't that mean that if Earth were a globe, that the method would not be reliable?
No, explicitly not, because it's based on two different timing predictions to verify the the difference in true position of the star. So no, that's not.
All right, so my question's still on the table.
Well, for photons and waves, for the purposes of this discussion, you could treat it either way, because all we're concerned with is the propagation time, which I think we would both agree is the same for either conceptualization.
Explain it to me like I just learned the thing.
Okay, if you conceptualize electromagnetic propagation as a ballistic projectile, little photon, then the speed's still going to be the same as if it's a wave propagating through a medium. So, for the purposes of this discussion, you can think of the light propagation however you want. Like I said, if you want to talk about that more in depth, that's an entirely different discussion.
So is it a particle or wave?
You can conceptualize it however you would like for the purposes of this discussion. I think that it is a wave, and you can go over various experiments for all that, but that is not the purpose of this discussion.
Yeah, it was regarding my question. Yeah, I think it's a wave too. I really am concerned if people think light behaves like a particle. Um, I
Well,
think
that's a
Einstein.
concern for another discussion. Does anyone else have any questions? Jesse, did you have another one, or was that it for that? If so, we can go ahead and wrap for the night, lads.
I do have another one, but we don't have time for it. So maybe maybe we can work through it another time or something. But I'll throw it out there. But I'm not expecting us to go over it. I really would like for us to go over together on figuring out what angle the method would give if Earth were a globe. My contention is that the Mount Rosa, for example, would have still given the flat Earth results, even if Earth were a globe. So
Interesting. Yeah, we will definitely come back to that.
and I think I could convince you too if we had, a half an hour. So
All right. Well, there will be a future celestial theodolite update here. When we continue it again, we'll definitely circle back to that.
I might see if Toon wants to do another one too. That was good.
Yeah.
This was
Sounds
a good
good.
conversation. It's good listening.
All right, excellent. So we will see you guys next time on Celestial Theodolite update number VIII, which is 9. Because we are on number 8 right now.
That's not how you do Roman numerals, bro. That's disgusting.
What is it?
I
IX? Is it
Yeah,
IX?
it would
I
be
have a
yeah.
I have a question.
I've heard it both ways.
Go ahead. What you got?
Alan, can you please give me an invite to Ether Cosmology, please? I've asked before. I'm not sure I got it. I may have missed it, but could you
Yeah,
maybe send me a DM
Yep, I will. I will
just so
talk
that I
to
have it
the
personally?
I'll talk to human resources and get that sent out to you. So
See if we can
tonight,
get.
Well, that would be great. Thank you.
tonight we're
Thank
gonna
you,
wrap
Alan.
up here. Yep, no worries.
I want
Tonight
one
we're
too.
gonna wrap up here with a view of where we're at. Oh, I can't video share with 25 more. All right, no worries, lads. But we are in the Salt Flats here. We're meeting up with Taylor and her husband. We're gonna try and do some celestial theodoliting tonight. I might do a little live stream here in about 30 minutes or something before the sun goes down, so you guys can see where we're at.
Alrighty.
But much appreciated
Well,
to
Alan,
everybody who contributed to the support of Ether Cosmology through the merch store. With that, we were able to buy our own C-Star camera. So we are going to actively participate in more celestial theodolite measurements and observations. And just shout out to everyone. And your guys' merch will be coming soon. All right.
Thank you, Alan. Thank you, Dr. Mike.
Shane, are you still there, sir? All right, Shane's AFK. I will wrap up the streams later on my end, but you guys are all free to discuss things willy-nilly. If you could, Geo, disconnect Shane from the thing there while I end the streams.
Also disconnect Bandy if you could.
Enjoy Utah, Alan.